Let's take a look at section 3.9, derivatives of exponential and logarithmic functions. First, we have a few rules we'll be using for this section. So there's our first two derivative rules. The derivative of the exponential function e to the x is itself e to the x, and the derivative of the natural log function ln of x is 1 over x. If you'd like proofs for any of these rules we're going to be using today, you can look those up in your textbook. Now for this second one here, we do have to add a little note. Since the logarithmic function has some domain restrictions, we need to emphasize that x is greater than 0 here. We also have some similar derivative rules for if the base we are working with is something other than the number e. So if b is any other real number, we have these last two rules. Now we do emphasize that b should be a positive value here for both of these rules. And for the last one, we are again dealing with a logarithmic function, which has the restriction that its argument must be positive. All right, now we're going to try a few straightforward examples before we move on to some that involve some techniques we've learned recently, like the chain rule and the product rule and the quotient rule. But first, part A here, all we have is a constant multiple, 3 times e to the x. So if we take the derivative with respect to x, the 3 stays, and the derivative of e to the x is just e to the x. Pretty straightforward. Another example, let's say we're taking the derivative of 3 plus e to the x. This time, the 3 is a separate term, so that goes to 0 when we take the derivative, but the e to the x remains. Now let's say instead I have the derivative of 3 to the power of x. Well, this time our base is 3, so we will be using this third rule here. So I keep the 3 to the x and I multiply by the natural log of 3. Now let's say I'm taking the derivative of log base 3 of x. Well, this would be our final rule. And we can see that will give us 1 over x multiplied by the natural log of 3. Let's move on to some examples that are a bit more involved. All right, we're now asked to find the derivative of y equals e to the power of 2x plus 1. So that means that dy dx, taking the derivative of the left-hand side, equals derivative of the right-hand side, derivative of e to anything remains, but then applying the chain rule, since my power is not just the variable x, I need to take the derivative of that power. There's the chain rule in action. So now evaluating that derivative, I get 2, and just rewriting that to make it look a little bit nicer, I have 2 times e to the power of 2x plus 1. Here's another fun example using the chain rule. Find the derivative of f of x equals e to the power of tangent of 5x. So e to the power of anything remains as is, but then using the chain rule, I need to take the derivative of that power. And the derivative of tangent of 5x, derivative of tangent is secant squared, but then we have another chain rule there. So secant squared of 5x, and then I need to apply the chain rule to that 5x inside of the secant. So you could do that all at once. I'm going to show all of my work here, but if you felt comfortable moving on to this final step, that is something that you could have done. So now I technically have my derivative, but I'm going to rewrite it just to make it look a little bit nicer. I like writing anything with a power at the very end. That way it doesn't look like the factors coming afterwards might accidentally be part of that power. I also like to write my constant factors at the beginning as well. So rewriting this, I'm going to say it's 5 secant squared of 5x, and it's very important to put the parentheses around that 5x there. Otherwise, this e might look like it's inside of that secant squared. And there we go. Now we want to find the derivative of y equals e to the x squared over x squared. So here we've got a quotient rule. We're also going to have a chain rule because of this added power. If you wanted to, you could change this from the quotient rule and rewrite it. And then you could use the product rule instead. But I'll go ahead and stick with using the quotient rule. So I encourage you to set this up on your own as I am setting it up, and then look back and compare. Now evaluating those derivatives. I have a chain rule right there. That's where this extra 2x came from, was the chain rule when I evaluated the derivative of e to the x squared. And the derivative of x squared is 2x all over x to the 4th. So we've got our derivative now. We're just going to clean this up and make it look a little bit nicer. Now there is some factoring I could do here. There's also some simplifying I could do here. So my numerator, both terms have a 2, an x, and an e to the x squared in common, leaving me with an x squared minus 1 all over x to the 4th. And then I can make one of those x's go away and write my final answer as 2e to the x squared times x squared minus 1 all over x cubed. All right, our next example here, we're asked to evaluate the derivative of ln of cosine of x. So the natural log function is my outer function. The cosine is my inner function for my chain rule. So starting with the derivative of the outside portion, derivative of natural log is 1 over x if we just had x, but I don't have an x, I have a cosine. And then I need to multiply by the derivative since I have a chain rule here. So the derivative of that inside function being cosine. Evaluating that, derivative of cosine is negative sine. So I have negative sine of x over cosine of x, which I can then simplify using my trig identities to negative tangent of x for my final answer. Now, if I want to evaluate the derivative of the square root of the natural log function, this time our outer function is that square root function. So if I wanted to, I could rewrite this as a power so that I can see that a little bit more clearly. Notice that power is on the entire natural log function. It's not just on the x. So I can bring that power down in front, subtract 1 from the power. So that's taking the derivative of that outer function. For my chain rule, I then leave the inside function the same and multiply by the derivative of that inner function. So evaluating that derivative and simplifying things a little bit. Everything can be moved into the denominator here. So that negative 1/2 power on that natural log, 1/2 power of course being the square root, and it's negative, so I moved it down into the denominator. And I don't like writing this x at the end because it might accidentally look like it's underneath that square root as well. So I'm just going to rewrite this one last time to make that a little bit more clear. 1 over 2x square root of the natural log of x. And our final example here is going to be very similar to the one we just did, but notice the difference. The last example had the square root on the outside of the natural log function. This time the square root is inside, so it's ln of the square root of x. If I wanted to rewrite this as a power to help, it would be the natural log of x to the 1/2 power. So we still need to use the chain rule here, but this time our outer function is the natural log. So I'm taking the square root of the natural log portion first, which my rule is 1 over whatever is inside of my natural log. Then I take the derivative of the inside expression. Evaluating that derivative, this 1 over x to the 1/2 stays. I use my power rule here, and I've got lots of algebra I can simplify here. Maybe you're like me and want to rewrite everything as a square root. If I make all of those powers positive, moving them down into denominators, I can multiply square root of x times the square root of x. Well, that just means that I have a single x there, and this is my final answer.